Hey there. We're absolutely swimming in data these days. Election polls, medical studies, you name it. And usually we just grab onto that one big headline number. But today, we're going to look past that single number and uncover the much, much richer story that's hiding just beneath the surface. Let's dive in. You see this kind of headline all the time, right? 45% of people are going to vote for so-and-so. It sounds so specific, so certain. But you got to remember, that number comes from a sample, just a tiny piece of the entire population. So how in the world can we know how close that is to the actual real number? And that's really the big idea here. The truth isn't some single dot on a map. It's more like a whole territory of possibilities. And lucky for us, statisticians have a tool that helps us map out that territory. And by the end of this, you'll know exactly how to read that map too. So, to really get a handle on the territory, we first have to understand why focusing on just a single point can be so, well, tricky. In the stats world, that single number, our 45% from the poll, has a name. It's called a point estimator. I mean, it's our best guess for sure. But that's all it is, one guess from a whole sea of other possibilities. There's this famous saying in statistics that just nails it. We know going in that our single guess is almost certainly not the exact true value down to the decimal point. So the goal isn't to be perfectly right. The goal is to be usefully close. So, what makes a guess useful? Well, think of it like a game of darts. On the left, we've got a great guesser. The darts are clustered tightly right around the bullseye. That's what we want, accurate and precise. But on the right, whoa, that's a bad guesser. The darts are all over the place and they're not even aimed at the center. That's not a very useful guess at all, is it? Okay, so if a single point is almost always going to be a little bit wrong, how do we get closer to the truth? Simple. We build a range around our guess. And this, my friends, is where the confidence interval comes into play. A confidence interval is basically our smarter guess. Instead of just throwing out one number, it gives us a lower boundary and an upper boundary. It's our way of saying, look, we're pretty darn sure the real answer is somewhere in here. It's a guess that's honest about its own uncertainty. Now, making a good interval is a bit of a balancing act. On one hand, you want to be really confident that your range actually captured the true value. But on the other hand, you want that range to be as small and helpful as possible. I mean, an interval that says the candidate support is somewhere between 1% and 99%, that's totally useless, even if you're 100% sure it's right. And this visual is just perfect for explaining what 95% actually means. Imagine you go out and you take 100 different samples from a population, and for each one, you build a confidence interval. That's what all these horizontal lines are. The 95% confidence part just means that we expect our method to work 95% of the time. So about 95 of those 100 intervals should successfully catch the real truth, which is that solid vertical line. It's all about the reliability of the process. So how do we actually cook one of these things up? Don't worry, we're not going to get lost in the mathematical weeds here, because the basic recipe is actually surprisingly simple. When you boil it all down, every confidence interval is basically this. You take your best guess, your point estimate, and then you add and subtract a little bit of wiggle room. And that wiggle room, that's the famous margin of error you always hear about in the news. So what makes that margin of error bigger or smaller? Well, it really comes down to three key things. First, how confident do you want to be? If you want to be 99% sure, you're going to need a wider margin than if you're okay with 95%. Second is the variation in your data. If your data is all over the place, you've got more uncertainty. And third, and this is the big one, sample size. The more data you have, the smaller your margin of error gets. All right, enough theory. Let's see how this incredible tool actually helps us make sense of some real-world questions. Okay, so check this out. Our first example comes from a Gallup poll back in 2020. Researchers wanted to figure out if there was a real difference in vaccine hesitancy between healthcare workers and other kinds of frontline workers. Now, if you just look at the point estimates, the raw percentages, it looks like there's a little bit of a difference, right? 34% of healthcare workers said no, compared to 32% of other frontline workers. That's a 2% gap. But here's the million-dollar question. Is that a real difference, or could it just be random chance from the samples they happen to pick? To answer that, we don't look at the two numbers separately. Instead, we calculate a confidence interval for the difference between them. And this is what we get. The range of plausible values for the true difference is somewhere between negative 2.1% and positive 6.1%. So what's the big deal here? The big deal is that the number 0 is sitting right inside our interval. And what that means is that a difference of 0 is a totally plausible outcome. So based on this data, we actually can't be confident that there's any real difference at all between these two groups. That 2% gap we saw, it could easily just be statistical noise. Now, let's contrast that with another example, just to see what it looks like when the story is a bit clearer. In this study, they were tracking the number of ships that passed by a power plant, and it compared summer days to winter days. So, after they crunched all the numbers, they calculated a 90% confidence interval for the difference in the average number of ships per day, and the interval they found was between 2.05 and 3.55. Now, see the difference here? The number 0 is nowhere near this interval. The entire range is positive. That gives us really strong evidence that there truly are more ships, on average, passing by in the summer than in the winter. We can be confident that this is a real, meaningful seasonal effect. And this all leads us to our final and maybe the most practical takeaway of all, the incredible power of just having more data. So at the end of the day, it's all about this trade-off. More data means more precision. It means a narrower, more useful confidence interval. It lets us be much more certain about our conclusions, especially if we're looking for a small effect. But, and it's a big but, collecting data costs time and money. So researchers are always having to balance that need for precision with the real-world costs of getting the job done. So, the next time you see a poll or a study or any headline that throws a single number at you, I hope you'll remember to ask, what's the rest of the story? What's the margin of error? What's the confidence interval? Because often, the most important part of the story isn't the guess itself, but the incredible range of possibilities that surrounds it.